So in this lesson, we're going to learn about isosceles triangles and the base angles theorem, which we'll incorporate into our proofs. An isosceles triangle is a triangle that has at least two congruent sides. So this is an example of an isosceles triangle. Traditionally, the two congruent sides are labeled or called legs, and a third side is called a base. And that's simply because we often draw an isosceles triangle so that the two congruent sides go up and the third side is sort of sitting on it like a base. It doesn't have to be in that orientation. I could turn this on its side and it would still be considered isosceles. I won't use these terms very often, but you should have at least seen them once. So the important thing about an isosceles triangle is, for triangles, if it has two congruent sides, it also has to have two congruent angles. And those come automatically. And that's simply due to the symmetry of the triangle. We could prove this using SAS, but it's visually very obvious. I'm not going to worry about a proof. If I have these two congruent sides to this triangle, there's a line of symmetry down the middle. So these two angles here also automatically are congruent. It's the angles opposite the two sides that are congruent. Now this has to be two sides of a triangle in order for this to work. I just can't have two random segments in a proof and expect to have two angles miraculously also be congruent. It only works if two sides are two sides of a triangle. But if it is two sides of a triangle, then you automatically get for free, if you know these two sides are the same, then you know these two angles are the same. And here's how we write this in proofs. So let's say I knew AB was congruent to BC for some reason. Maybe it's a given, but it could be any other reason. I could prove it using some other fact. Then, because AB and BC are two sides of this triangle, I automatically get for free, due to this fact about isosceles triangles, which is called the base angles theorem, that the opposite angles, angle A and angle C, are also congruent. And what I want you to write for reason here is I want you to draw a little picture of what you've used. This is my little picture for the base angles theorem. Two sides in a triangle congruent implies the opposite angles are congruent. This also works in reverse. You can go from two angles being the same and deduce that two sides have to be the same. So for example, if I had this triangle XYZ and I somehow prove, or I'm told as a given, that two of the angles are the same. Maybe I know angle Y is congruent to angle Z here. For some reason, then I may deduce, due to this base angles theorem, that the sides opposite these angles must also be congruent. So that would be XY congruent to XZ here. And again, we draw a little picture for the reason. Angles the same in a triangle implies sides the same. So let's see how you could use this in a proof. Here's my example proof I'm going to do. I'm given this information and I want to prove AB is congruent to CD. So I'll mark my givens. I have AZ congruent to DZ. I have angle AZB, that's this angle here, congruent to angle DZC. And I want to prove AB is congruent to CD. Now here's an example where you can't just use the base angles theorem. Here I have two angles the same. But I can't just say, oh, that means these opposite sides are the same. The base angles theorem only works if the two angles, I'll go back to the sheet here, if the two angles are two angles of the same triangle. So these two angles are congruent, but they're not two angles of the same triangle. This is an angle of two different triangles. So if I could somehow prove that this triangle here were congruent to this one, then I could deduce AB would have to be congruent to CD because of the corresponding parts of those triangles. But I don't have any other information. All I have is angle side. this is where the base angles theorem will help me out. I notice, oh wait, AZ and DC are two sides of this big triangle in the picture. And so when the big view, AZD is a big isosceles triangle in this picture. And because this big isosceles triangle has angle A, these two sides the same, that means I can go across from those two sides and deduce that this angle here at A has to be the same as this angle here at D. And then this forms the final mark in an ASA tick mark pattern, because in addition to A and D being angles of this big triangle, there are also angles in these two separate little triangles. A is an angle of angle AZB, and D is an angle of angle triangle DZC. So here's how this would look if I wrote it up. I'm going to prove that the two triangles here are congruent. I'll call it ZAB and ZDC. Make my box bigger. This is going to be an ASA proof. One pair of angles is the given pair up here. Angle AZB congruent to angle DZC. That's a given. That's one of my A's in the ASA, pair of congruent angles. The pair of sides is AZ and ZD, or AZ and DZ as I wrote in the givens. And then the last pair of angles in my ASA is this pair that I deduced because the big triangle is isosceles. And when you use the base angle theorem like this, you have a two-step process. You say, because I know these sides are the same, I know these angles are the same, or the other reverse if you're going from angles to sides. So this is going to go into here. But above this, I need to put what isosceles triangle let me make this deduction. So, and that was AZ and ZD again. AZ congruent to DZ. So notice we're using AZ congruent to ZZ twice in this proof. And there's nothing wrong with that. That's perfectly acceptable that I might use a fact in two different ways in a proof. I use AZ congruent to ZZ directly to prove the triangle is congruent in the ASA pattern. I also used it to deduce that angle A and angle D are the same using the base angle theorem, and that gave me a pair of angles. And here I've assembled my angle side angle congruences. So that tells me these triangles are congruent. And then because the triangles are congruent, I may deduce that AB and CD are the same because AB and CD are corresponding sides of my congruent triangles.